So now we are going to discuss systematic layout planning. So this is an approach that is used to design process layouts. So this was developed by Richard Muther. Most widely used layout planning approach. It is most applicable to process layout design. And it is most appropriate for designing a new plant. It assumes that the plant location has already been decided, because that is an important decision in layout planning. So we have to first decide the location. And there are many factors actually that help us in deciding the location of the plant. So once that has been decided, we can use this systematic layout planning approach to design the layout. So I hope you have studied different methods of selecting facility location. So one of them is center of gravity method, but there are other methods as well. So there are 9 steps in systematic layout planning. First, we have to determine requirements and collect data. Then we have to analyze material flows. Step number 3 is to define activity relationships and develop activity relationship chart. Then we have to construct activity relationship diagram. So these are 2 different things. We have to determine space requirements. Then we have to construct space relationship diagram. Then we make adjustments and add allowances. And then we make block layout. And finally, detailed layout. So we will discuss this approach step by step. So step number 1 is to determine requirements and collect data. Starting specification in plant layout design has some important aspects. One of them is the product or set of products that will be produced. So what product you will be making in the facility. So it could be a single product if it is a dedicated production facility, or it could be a family of products. And the second important consideration is a particular set of manufacturing or assembly processes that will be performed. So both are important, the product that you're going to make and the processes required to make that product. And third point is the quantities. The quantities of parts and products that you are anticipating you will be producing. So you have to analyze these requirements. So there is a simple rule of thumb to actually list down the requirements. So that is called PQRST approach. The P stands for the product. P is for product. What products you are going to make. The Q is the quantity. How many of each product? R is the routing. That is the sequence of processes through which parts and products will be routed. That is also important. S is for supporting services. The utilities, the restrooms, the offices, cafeteria, etc. And T is for time issues. How many shifts per week will be used? And by when must the building project be completed? Now, this is very important, that designing a layout and constructing the facility according to the layout is also a project. So that is quite interesting. So it is possible, regarding the first point, the P, the products that the organization is going to make, that the organization might be producing an average quantity of a wide range of products. Q is the quantity, P is the number of products, different types of products. So curve indicates that multiple products with medium quantities are going to be produced. But this situation is quite different than this, where one product is going to be made, only one product, P is for product, in large quantity. So the layout requirements in this case will be very different than this. So you could visualize that this is a typical scenario. The one shown on the slide is for a process layout, and this one seems to be a candidate for a product layout. But the requirements will be totally different. The requirements for the layout is now requirements related to routing. Routing is through what manufacturing processes will the product or parts be routed. It can be used to plan arrangement of equipment and their corresponding departments. So this is a very important piece of information. Sequence of steps. What will be the first process to be performed on the product, the second process, and so on. Now, there could be different sources of data on the routing. One of them is routing sheet. It indicates the sequence of machines that the part must visit during its processing. So this is a typical routing machine that mentions some details about the part and the material that is required, the size of the starting material. And then there are sequence of steps, the description of each step, the department in which that step will be performed, and in that department, what is the specific machine on which that operation will be performed, the tooling required, jigs, fixtures, dies, and molds, the setup time, standard time, and of course, there could be other details as well. Then the requirements for supporting services, additional provisions that are not related directly to the product or its manufacturing. For example, utilities like electrical power requirements, water supply, ventilation, air conditioning, etc. So you might be using pneumatic machines, so you also may need some source of power for compressed air. The supporting services could also include offices, the locker rooms, cafeteria, washrooms, parking area, and so on. The time requirements. Now, there are two important aspects regarding time requirements in layout design. One of them is the time issues related to the plant operation. Will it operate one 8-hour shift, 5 days per week, or it will operate, for example, in 2 shifts, or will it operate 24 hours a day, 7 days a week? Now, this is the typical case, of course, for continuous manufacturing, the 5th process that we saw. But for discrete manufacturing, either the organization is using 1 shift or 2 shifts. Rarely they are using 3 shifts. But why this is important? This is important because it will help you decide the space requirements. For example, if a plant that operates 3 shifts per day needs only 1/3 the floor space and 1/3 the number of pieces of equipment as compared to a plant that runs 1 shift per day. So this is why this is important to decide that in general, whether you will be operating 1 shift, 2 shifts, or 3 shifts, because that will help you decide the space requirement. So this is one time-related aspect in layout design. The second aspect is the time requirements to design the layout and construct the building. So as I mentioned that the layout design and construction of the facility is a project itself. And we saw that there are 3 important aspects in projects. They are time, cost, and scope. So time is also important with respect to the layout design and construction of the building. So this was the first step in systematic layout planning. So if you have any question, you can ask. The second step in systematic layout planning is to analyze material flows. So what are possible charting techniques to analyze material flows? So we have discussed a number of charts and diagrams that help us analyze the material flow, to help us analyze the frequency of flows, the distance that the part is traveling, and so on. So one of them is operations process chart. It shows sequence of processing, assembly, and inspection operations for products. We saw it in detail. Flow process chart can be used, that shows processing steps and other details for parts production. We can use from to chart, that is also called travel chart. So that shows quantities and directions of material flows between departments. We also saw the spaghetti diagram, so that can also be used if you can visualize the flow of the part if it is a totally new layout. And part routing matrix can also be used. We will see how it looks like toward the end of this lecture, but you can, of course, use other charts and diagrams that may seem relevant. The step number 3 is to define activity relationships. It indicates relative need to place activities or departments in close proximity to each other. So how important is it that two departments should be close together? So we assign closeness rating, and you could use different scales for this closeness rating. The one that is mentioned in the Groover's book and that we are going to use is this AEIOU type rating. So A stands for absolutely necessary for departments to be next to each other. E is especially important. I is important. O is ordinary, having ordinary importance, and U is unimportant. So you could say that it is something like a scale of 1 to 5. So A for 5, E for 4, then 3 to 1, something like that. X is undesirable to locate departments near each other. So in this case, if we are assigning X rating, then those two departments should not be adjacent to each other. So we will see how we can use this rating. But first we have to ask, on which factors does this closeness rating depend? There are different factors. Perhaps the most important is material flow. The material flow. So depending upon the frequency and the quantity of the material flow, we can assign high closeness rating. So if there is a lot of material flow between two departments, they should be close to each other. So that is the most important factor. Just remember that process layouts are used for job shops and batch processes where there is a lot of material movement, a lot of transportation that we want to minimize. So if the two departments between which there is a lot of movement, if they are close together, then the cumulative material flow will be minimized. So the transportation time will be minimized. So ultimately, total manufacturing lead time will be reduced. So we will be having high inventory turnover, high efficiency, and so on. But there could be other factors as well. For example, need for contact between personnel. So there could be some staff that is common between two departments. So they should be close together. Use of common equipment could be a reason. Sharing of common records, sharing of supervision or technical staff. So one manager is looking after two departments, so they should be close together. The use of same utilities. So these are some additional factors that should be considered. So they are the factors that make two departments close to each other. Then there are factors that help us to decide that two departments should not be close to each other. So there could be some negative factors like high noise, emission of fumes, or some other factor that helps us decide the location of a department to be far away from other departments. So these 7 and 8 are reasons for separating a given department from others. So X closeness rating should be assigned. So we use activity relationship chart to show this closeness rating. For example, in this case, we are having 6 departments. So for example, production and stockroom, they are having a closeness rating of A. So we will simply match the two columns, you can say, and where they match, we write the rating there. So it is very important. It is absolutely necessary that production and stock room should be adjacent to each other. Similarly, for example, if we see the relationship of production and the locker room, we are having a rating of E. So it is also very important that production and locker room should be close together, but this rating is slightly lower than the rating of A between production and stock room. So you could assign the rating this way. So this is activity relationship chart. So what is, for example, the relationship between production and offices? So that is a rating O. Relationship between production and tool room. So that is a rating A. Production and tool room. So we will simply match the columns. So that is a rating A. Relationship between offices and locker room. So you could see that offices and locker room are having a rating of E. So how to assign closeness rating? So there are different ways. We can assign this rating based on judgment and experience. And if rating is based primarily on material flow, then we can simply use conversion to assign the rating. So these are the steps. First, we have to find the highest value of material flow between two departments and divide by 4 to obtain 4 ranges of material flow values. Now, values of material flow in the highest range are converted to an A closeness rating. Values in the next range are converted to E rating and so on. And the U closeness rating is assigned to the pairs of departments between which there is no material flow. So we will see how we can apply this conversion in the following slides. But if you are taking the material flow to be the only or the most important factor, then you can use this approach to assign the ratings. So here is the example that we will use. The anticipated material flows between 6 production departments are given in the from to chart or the travel chart. There are 6 departments: receiving and storage, finishing, production, tooling, assembly, and packaging and shipping. The values in the table indicate the number of unit loads that must be moved per day and their direction. So this is a travel chart or from to chart showing the number of unit loads. Convert the material flows to closeness rating and show them in an activity relationship chart. So for example, the movements from department 1 to 2, that is receiving and storage and finishing, is 27 unit loads, and from say 1 to 4 is 15, and say from 1 to 5 is 110, and from 5 to 1 it is 10. So we have to add them up. So from department 1 to 5 it is 110. So forward movement it can be called, and from 5 to 1 it is 10. So that is the backward movement. So take some time to add these flows and assign the closeness rating. So the flows, number of flows between department 1 and 2 are 27, and there is no flow between department 2 and 1. So total will be 27. Between 1 and 3, there is no flow, and between 3 and 1, there is a flow 82. So total will be 82. Just focus on this arrow that this is showing the two-way flow from 1 to 2 and 2 to 1, from 1 to 3 and 3 to 1, and so on. Similarly, the total flow from department 1 to 4 is 15, and no flow from 4 to 1, so total will be 15. From 1 to 5, 110, from 5 to 110, so total will be 120. And you can see for other departments as well. So for example, from 2 to 5, the flow is 42, from 5 to 2, it is 26, so total is 68. So this table is filled in this way. Highest value is 120. Divide that by 4, we get 30. So we assign a rating of U for 0 loads moved between two departments, O rating for loads from 1 to 30, I rating for loads from 31 to 60, E for loads 61 to 90, and a rating of A for loads 91 to 120. So in this way, we can fill this table. For example, the total loads between 1 and 2 are 27, so 27 lies here. Rating of O is assigned. Between 1 and 3, there are total flows of 82, 82 lies here. So a rating of E is assigned. Between 1 and 5, there are total 120 loads, so a rating of A is assigned, and so on. So for example, between 4 and 5, there are 30 flows, so 30 lies here, so a rating of O is assigned. So using these ratings, we can fill this activity relationship chart. So for example, between department 1 and 6, there is a rating of I. So that I is here between 1 and 6. Between 2 and 5, there is a rating of E. So 2 and 5. And between 3 and 4, there is a rating of O, so that is O. And you could cross-check others as well. So the next step is to make activity relationship diagram. So this was activity relationship chart. So using this chart and these ratings, we can construct activity relationship diagram. So this diagram is actually graphical means of displaying the closeness ratings among pairs of activities or departments. It uses nodes to represent activities, and nodes are connected by lines indicating the closeness rating. Now, there are different ways actually to draw these lines. So for example, for a rating of A, you could use 4 lines between two departments if they are having a closeness rating of A. You could use 3 lines to show a closeness rating of E, 2 lines for I, 1 for O, and no line for U. And you could use a wavy line showing a rating of X. Or you could use different colors, or you could use different thickness of the line. So there are different approaches that can be used. Now we are having 6 departments. So if you recall, or you could cross-check from your table that the rating between 1 and 5 was A. So we have shown that using these 4 lines. And there was a rating of U, unimportant, between department 2 and 3. So there is no line between department 2 and 3. And there was a rating of O between department 3 and 4. So that is shown using 1 line. A rating of E is shown using 3 lines, and so on. So this is one of the ways. But instead of, say, using 4 lines, you could use 1 line that was thicker than the others, but that would be difficult to interpret than this one. A good approach is to do both things, to use a certain number of lines as well as different colors. So for example, these 4 lines could be drawn using green color, 3 lines using say blue color, 2 lines say using orange color, or and so on. So you could use both the number of lines and color to better visualize. So this is activity relationship diagram. So we can visualize the importance rating with the help of lines instead of numbers, and that is shown on a sort of very roughly drawn flow diagram, or you could say a very roughly drawn layout. Actually, it is not a flow diagram as well. It's a rough layout that is showing the departments in a certain sequence, so they are in a series 1 2 3 4 5 6, and the closeness rating. Now we could rearrange these departments to make a better arrangement. Now, what is meant by better arrangement? We want to minimize these crossing lines. So, for example, we could actually cross-check the total flows between 1 and 3 and between 3 and 6. So these are called non-adjacent loads. So we want to minimize these non-adjacent loads. So we could shuffle these departments. For example, 3 could be here and 2 could be here, and you could play with this grid and you could make an arrangement. So this is just one example, and you could make a different arrangement than this. So ultimate goal is to minimize these non-adjacent loads. So of course, this line is showing a certain number of loads. So we could see from the table how many loads were there between department 3 and 4. So we want to minimize these non-adjacent loads. So you could play with this grid and make a certain arrangement, calculate the non-adjacent loads, make a new arrangement, and calculate non-adjacent loads, and see which arrangement gives the minimum number of non-adjacent loads. Ideally, there should be 0 non-adjacent loads. And there are actually different software that can help you do that. And because practically you could have many departments in the organization instead of 6. So you could use those software, or you could use trial and error to see which arrangement gives minimum number of non-adjacent loads. So the next step is to calculate the space requirements. You could see that each of these boxes has the same size. But actually we need different areas, different space for different departments. That is the next step. Once we have come up with a certain arrangement of departments with respect to each other, next step is to calculate the required area. So that is called to calculate space requirements. All blocks in the activity relationship diagram, as we saw, were of the same size. So objective of this step number 5, is to determine area requirements for each activity or department. So there are certain simple steps to follow. The first one is list all workstation types. How many workstation types will be there? For example, if we are going to have 4 types of machines, there will be certain lathe machines in our department, in the organization. In that certain department, actually, we are talking about a certain department at the moment. Milling machines, grinding machines, for example, and shaper, or there could be some other workstation. So we have to identify the types of workstation. So how many types of workstation will be there? 4, 5, 6. We have to list them down. Then we have to determine the floor space requirement for each station type. How much area will each lathe require? How much area will each milling require? How much area will each grinding machine require? So AI is the area of station type, and it is possible that there could be machines of different sizes. So we could have then different areas actually to add. So each workstation will require a certain area. So that is AI. So workstation 1 will require certain area A1, workstation type 2 will require a certain area A2, and so on. So this is step number 2. So this is the covered area, the floor area that workstation will require. And it is better to add the area for the workers, work in process, and so forth. So that will give you a certain area for that workstation. So this area of the machine, A1, A2, A3, A4, plus some area for the workers or work in process. So in simple word, you could say that this area includes everything that we have mentioned. So this includes the area of the workstation plus some additional area for the workers, work in process, and so forth. So I hope it is straightforward. The next step is to calculate the number of workstations. How many lathes we will require, how many milling, how many grinding, how many shapers we will require. So there is a simple formula to calculate number of workstations. And that is equal to workload divided by available time. Workload divided by available time. So how many hours that specific workstation will be in operation. And that will depend upon the demand, right? So for example, on lathe, we have to make 100 products and each will require 10 minutes, just for example. So workload will be 1000 minutes. So that will be equal to 1000 divided by available time. So we could be making these calculations for a day, for a week, for a month, for a certain time period. So for example, if this demand is for a certain period, say for a quarter, then we have to take available time for a quarter as well. If this workload is for a month, then we have to take available time for a month as well. If it is for a day, workload is for a day, we have to take available time for a day as well. So we have to keep the units consistent. So if the workload is say 1000 hours, and for example, available time during that duration is 200 hours, then we will require 5 machines, 5 workstations. So you could take this workload and available time, both are actually times, or it could be actually demand over capacity. So then both demand and capacity will be in terms of number of units. So both mean the same thing. The point is whether you are taking workload in terms of time or number of units, and capacity in terms of number of units or available time. But as we are discussing process layout and each product has different requirements, I mean, each product has a different quantity to be made. So it is better to use the formula that is mentioned here, that is to take workload and available time, both in terms of time. For example, in hours of work per period or hours available. So that will give us the number of machines. Now, of course, if there are more than one types of products that are being made or that have to be made on a work center, then of course the workload of different products that are to be made on that work center will be added. So quantities multiplied by time, they will be added. So that will give us the total workload if more than one products are to be processed. So this number will change then. Once we have calculated the area of each workstation and number of workstations, then we simply multiply the two to find the total area required for that workstation. For example, we will be able to calculate total area for lathe, for milling, for grinding, and for shaper. So that will be equal to, for example, number of lathe machines required multiplied by area of one workstation, because workstation included the area of the machine plus some additional area for the worker, for the raw material, and so on. So we will be able to calculate, say, four total areas in this case for each type of workstation. And I repeat that that total area will be equal to number of workstation multiplied by area of workstation. The total area of the department will be equal to sum of these different total areas of different workstations. So that will be equal to departmental area. So we will be able to determine total area in each department by summing areas of all station types in that department. So what were the steps? First we listed down the types of workstations. Then we calculated the area required by each workstation. That was the floor area required to install the machine plus some area for the worker, raw material, tools, etc. Then we calculated the number of workstations required. So that was equal to workload divided by available time. Multiplied the number of workstation with the area of each workstation to calculate total area of each workstation, then added the area of different workstations to calculate the departmental area. If you have any questions so far, you can ask. Step number 6 in systematic layout planning is to draw space relationship diagram. So in the previous figures, we were drawing the departments with the same size. But now once we have calculated the area of each department, so we can draw the departments according to scale. So this is basically space relationship diagram is basically extension of activity relationship diagram in which nodes representing departments are now assigned areas that are proportional to areas calculated in previous step. Shapes of nodes may be changed to fit the nodes into the diagram. So we could be using rectangular blocks instead of square, but relative positions of blocks should remain as in the last iteration of the activity relationship diagram. So this is the same diagram, but departments are drawn according to scale. So this department 4 had an area of 98 meters square. So according to scale, this square should be equal to 98 meters square. This had an area of 349. So this square should have an area 349 and so on. Then in step number 7, we make some adjustments and add allowances. So there are actually different allowances that we could add. So they will increase the area that we calculated previously. So we could add allowance for personal requirements like restrooms, locker rooms, food services, plant entrances and exits. We could add allowance for material handling methods, like, for example, forklift trucks or trolleys. Storage facilities also require some area. We could add a separate department for storage, or if the storage takes place within the department, then we will add some allowance for that. The allowance for aisle space, offices, and so on. We could use a rule of thumb, and we could, for example, add a certain percentage of the area as an allowance. For example, whatever area was calculated here, we could add 25% of it for all types of allowances. Or we could, of course, see the specific requirements of each department and add allowances accordingly. Then in step number 8, we have to develop a block layout. Here we develop alternate layout plans based on space relationship diagram. And here we check different shapes and aspect ratios. So simplest shape is, of course, a square, but we could see rectangles or different other shapes. And depending upon, actually, one important factor that comes into play here is the available area. What is the available area and what is the shape of that area? That is also important, and that helps us decide actually a specific block layout. And based on different options available, we select the best option. And we may have to compromise between between competing objectives and modifying consideration and practical limitations. One of those limitations is available area where the plant is being constructed and shape of that area. So this is the block layout. So you could see that for certain departments, instead of square shape, we are having rectangular shape. And we could slightly adjust the position of the departments as well. So instead of having this orientation of department 4 and 2, we could have this one. We could leave some space over here and some space over here. So this is where we have to involve a lot of discussion, a lot of trade-offs, a lot of practical implications. And once we have made the block layout, and you could see here, important point, that final block diagram adjusts the block diagram for the desired shape of the building. So that is important. So here is another example. We are having 5 departments here. So this initial block diagram can be merged in different ways. And this is one of the options. And you could see that department number 2 here is sort of at the boundary of department 1 and 4. That is at the intersection of department 1 and 4. So of course, depending upon the shape of the building that you require and available area, and of course, based on the closeness rating, you could have different possibilities. The final step is to develop detailed layout. So filling in the block layout with the details of how each department will be arranged, locations and areas of workstations within each department, aisles, department offices, storage areas, everything is shown. So layout design provides a check on the original calculations. If details do not fit into the space correctly, then there may be an error in the original space calculations. So here is an example. You could see different departments: receiving and inspection, warehouse, milling, and so on. And you could see the aisles between departments. And actually, you could show, it's better to show the position of machines and equipment within each department as well. That is not shown here in this detailed layout. So these were the steps of Muther's systematic layout planning. If you have any questions, you can ask.